Okay, let's go ahead and get started today. This is class 12. We're going to do a little more with string functions. And I also want to cover something that seems to have been confusing for some of you, and that's how you organize your code as far as writing functions. So let's get started with a little more with the strings first. So previously, to quickly review, strings in C evaluate whether they're in double quotes or whether you're storing that in a character pointer, meaning holding the address of that string in memory, or whether you are creating a character array where you use the name of the array by itself, which evaluates as an address. All of those cases where we have something like a string, they're stored as a pointer to that place in memory or the address of where in memory that string starts. So in other words, whenever I create a string, it lives somewhere in memory. It has to. It's the way the computer works. And it evaluates whether, even if you put a string in double quotes, it evaluates as where does this start in memory. If you have storing that in a variable as a character pointer, it's the address of where in memory it starts. If you have an array, use the name of the array by itself, it's where in memory that address is where that starts. So the data at that address, however, should be terminated by a null character. That's how C knows when the string is done or when the end of it is. So in other words, you start at the beginning, you go through until you see the null. The null is kind of like, you can think of it as a sentinel or a kind of way to demarcate the end of the string, or you can consider it a terminating character. But that null character is what tells C that's the end of the string. So in other words, we have the address up through the end of the string. And hold on one second, a dog is eating something plastic. So hold on, I'm going to pause for just a second. Okay, we are back. Now, moving on from here, that null character signifying the end of the string. So a string is an address stored as the address of the beginning, and then characters through memory going all the way up to the end. Now, let's to kind of further clarify that and make that a little more understandable, let's look at a few examples. So here in my program, if I said char str16, this is making a character array that has 16 bytes reserved for it, space for 16 characters. And only 16. So one of the things about C is it's not like Python where you create a string and it has an object and that object has methods and there's all this other stuff going on in memory. In C, if I create this character array, I get exactly 16 bytes. There's no hidden structure to it. There's no methods. There's no, again, C being kind of that mid-level to low-level operating systems programming language, a systems programming language. It was designed to be as close to the hardware as possible. So when I say, give me an array of 16 characters, that's exactly what I get, and all that I get is an array of 16 characters. And when I use this name str by itself, it just gives me the address of where that block of 16 characters starts in memory. So let's look at what that would look like in memory. So in memory, that would look like 16 bytes, and I have this divided into two things. This one is going to be the character representation. This one is going to be the same 16 bytes, but represented as a number, as you'll see. But right now, we have no idea what those are in memory. Those could be all kinds of different random values because C does not initialize these for us. It basically says reserve 16 bytes. Whatever it happens to be in those happens to be in those. So looking at the output of that, as we'll see in a second, that there could be just random garbage in there. So remember that the uninitialized variables are not initialized, so we have no idea what's in those 16 bytes right now. Could be zeros. Could be other random garbage, could be stuff left from some other program that ran in the past. We have no idea. All right, so here's another example. And this one is, now we're initializing that array of 16 characters, and I'm putting the string hello world in there. But notice that this has 16 spaces reserved, but if we count the number of characters here, H, E, L, L, O, that's 5, spaces 6, 7, 8, 9, 10, 11, 12. So there's 12 there, plus the null character that's automatically added to the end, the ASCII character 0 added to the end, that's 13. So we're going to have several bytes at the end, 3 bytes at the end, that are not initialized. You're going to have random junk in them. And so here, is what that would look like in memory. So going through memory at index, or the first address, the H, and the E, and the L, the L, the O, and then a space, and the world, exclamation mark, and then the null. That null gets automatically added. And then we have this stuff after the null that's random garbage. Now, some compilers will automatically zero things when we initialize an array. Some of them will just be random garbage. But you can't, if you're making a cross-platform program, you can't rely on these being zeroed out. You can rely on that null being there automatically, but not necessarily any of these. And this is what the values, the decimal values, would look like in memory. So in memory, the phrase hello space world, exclamation mark, is really stored as just a bunch of binary numbers. And really, this is not even decimal. They'd just be binary representations of these. And then a 0 byte at the end. In other words, all 8 bits zeroed out to say that's the end of the string. And then what's after that null? Might be 0, might not be. So only the initialized parts are initialized or can be relied upon being initialized, plus the null character at the end, but not anything after that if the sizes don't match. All right, let's look at one other example. So here's an example with a character array of 16, where we said hello big world, exclamation mark. And if we count up the number of characters here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have exactly 16 characters, which means we do not have room for the null character at the end. And some compilers this will generate an error, some it will generate a warning, some it will just compile. But we've got to be cautious here because we did not leave room for the null character. So in memory, that'll look like this with no null at the end. So if I were to print this out using something like printf, or I would use a string function on it like StringCopy, there's no room for a null terminator, which means that when it goes to print this, the way printf works, or any of those string functions work, is they run through the stuff until we get to a 0 character, and we don't have room for the 0. So it could run off in memory and keep printing other junk, or it could go out of the memory bounds reserved for the process if we're in user space mode instead of kernel mode, and that could run off the end of that string and then cause an illegal operation in our program, and our program would crash. The operating system would kill our program for trying to use memory that was not allocated to it. So we got to watch out that whenever you allocate space for a string, make sure you have enough to have the null character at the end of it. So in this case, no room for the null terminator. And we have to, it's up to us, the compiler is not going to make that bigger for us. At runtime, it's not going to resize it. Again, C is a very close to the hardware language, and basically it's not going to do those kinds of things for us. So we have to be the ones that take care of that. We have to make sure we leave room for that null at the end. All right, so let's write a simple program and illustrate this. We're going to go through a few of these here. So here's a program, relatively simple. You could type this in if you want, but let me go through what's going on here. So the first line here, we're including standard io.h. That's just to get the printf function prototype, so we can use printf, which is a standard library function. So we're including that to get that header, or that function prototype, in that header file. And here's my main function, which is where the program starts up. And then down here, we made it a character array of 16 bytes, just like we did in the first example, but notice I did not initialize it. I have int I, also not initialized. And then I print out, here's my printf, index, and then \t is an escape sequence. Notice the \t there. That's a tab. So we're printing out index, tab, pointer value, tab, character, char, tab, decimal, and then a new line, which will go to the next line. So we've printed out those things, and that's kind of printing out the top of this table. And then I'm entering a loop that goes for I equals 0. So we're going to start I at 0. We're going to run while I is less than 16, and we're going to increment I at the bottom of the loop every time. Now what are we going to do in the loop? We're going to print out a decimal integer, a tab. So that's going to be underneath the index one, and then underneath that, %p, which is a pointer, address, print specifier, and then a tab, and then a character specifier, which is a single character like A, B, C, exclamation mark, whatever, and then a tab, and then another decimal integer, which is going to be the actual contents of that variable. So this is kind of what we had on that previous chart back here. We're printing this out like this, but going down and we're also printing out the addresses those are at. So here's I, the index value, so that would be 0, 1, 2, 3, 4, 5, all the way to 15, and then the address of that character that we're at, and then the character representation, and then the decimal representation. Now let's look at what the output of that would be. So here's what the output would be. So you notice we get 0 through 15, and here are the addresses. Notice this is just a number. Notice it increases by 1 every time. So going through memory, so these are like the mailbox or the memory box addresses where all of that data actually lives. And if you run this different times, you'll get different addresses in here. Also notice that because I did not initialize this, there's just random garbage in there. There are some zeros, but there's also a negative 112, which is, I suppose I should have printed that out as an unsigned integer here. But you'll notice there's that. There's a 6, there's a 64, there's another 64, there's a 5, there's a bunch of zeros. So this is just random garbage that happened to be in memory. Now what's interesting is that when you create programs like this, if you just allocate memory in your C program and print out the random garbage that happened to be in there, sometimes you'll see things that were from other programs that ran in the past. Sometimes you'll see strings of things that were printed out. Sometimes you might even see things left over in memory that were where people typed things in before. And that can be actually a security hole for a program, that if you run a program and it has sensitive stuff like passwords or credit card information, and you have a program that had somebody typing those in and storing them, you might want to clear out or zero out that memory before the program ends, because otherwise it could end up where somebody could see that in their program when they run that. And there's we'll talk a little more about this later, but there's like a form of attack called memory phishing, and that can happen even if you're on a shared computer system where multiple people are logged in. If you can allocate memory, and you could look through that memory and see what's there, and you might get lucky and see something that somebody didn't want you to see, or something that would allow you to do something with that. So anyway, just notice that we have no control over this because we're not initializing. We're just getting whatever memory the computer system gave us, and these are the addresses that it is at. All right, let's look at another example. Now this one, I initialized the string with hello world. So that's the only, and actually there's a bug there. There's an extra semicolon. Let me fix that. I don't know why there's a semicolon there. Okay, so this one we're just initializing to say hello world. And other than that, the rest of it's the same. So same program, the only thing we did is initialize that. So let's look at what the output of that is. So here's the output of that. Hello space world, exclamation mark. There's my null. And let me back up for just a second. Notice the null. There are nulls in here in this one. But since we did not put a string in, notice that if I were to print this out, I would just get random garbage, but it would stop there. That's actually acting as the end of the string, but that's just by luck. But in this one, that null right there was put in purposefully by the compiler to indicate the end of the hello world string. And these ones here are either purposeful or accidental, depends on the compiler, but it just happens to have 0 in the space after that. But that one will always be a 0. These ones might not. All right, let's look at another example. Now this one, I am taking this character array, 16 characters, putting hello world in it, and that's going to have the null, but then I'm doing a string copy. All I've done is I've added this string copy line. I'm saying, hey, string copy into this array, this space in memory, the word help, exclamation mark. So that's going to get copied into this array, and let's look at what that winds up in memory. Remember how string copy worked. It basically says, go to this address and take characters from this address and move them into that one at a time until we get to the null, and then copy the null, and then stop. And if you remember last class, we created our own implementations of string copy and made actually 4 different versions of that would copy a string from one place in memory to another place. But this one, we're using the one that's built in to the standard library. To use that, we needed to include string.h to have the function prototype for that at the top. So there that is down there. So let's look at what that does to memory. So notice there is now the help, exclamation mark, with the null that was copied in. But notice the world part and the null was still in there. This doesn't completely erase everything that's in that whole thing, because how would it ever know how to? oops, it basically just copies characters from this until it gets to the null, and it copies the null, then it stops. So we copied in the H, and then went to the E, and then the L, and the P, and the exclamation mark, and then the null, and then it stopped. So it left the other stuff in memory in there that was in there from before. So you'll notice how kind of bare to the memory this implementation is, that we're just moving bytes from one place in memory, one at a time to another place in memory, until everything has been copied over. All right, let's look at one other one. All right, so here is hello world exclamation mark put into this character array that's 16 spaces. Remember, that left 3 spaces at the end after the null that were not really part of this hello world message. And then I do a string copy of this string. And if I count the number of characters in this, let's do this. So all I did was change this string that I was copying in from help to something else. So this one is this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we got to 16, but now we're copying more past that. So this is only big enough for 16, and we're trying to copy 16, 17, 18, 19, 20, 21, 22, 23, plus the null. We're trying to fit 24 characters into an allocated space of 16. And again, C being kind of trusting the programmer, it says you want to stick 24 things into a space that can only hold 16. We'll let you run right off the end of that space in memory. So what's going to happen is, notice I'm only trying to print out the top 16, but what's going to happen when we try to copy that extra stuff into that space? Let's look at what the output would be. So notice that it did copy the stuff in there, this space, string, space, is, space, T. There's the T for the too big. There's no null at the end. And since the C only cares about, hey, I'll copy this till I get to the null at the end, it went off of the end of the memory. And you'll notice that the compiler said, hey, I detected what's called stack smashing, which is essentially, since this is a local variable, we went off of the end of that over the top of other parts of memory that were being used for something else. And that got detected, and the program got terminated because we went outside of the memory that was allocated for that. So realistically, we walked off of memory into other parts of memory and did something bad. The runtime detected that and killed the program. So notice it says aborted core dumped. Dumping the core basically means dumping the image, so you could actually analyze that to see what went wrong. But notice that that's not really C language that's doing that checking. It let us run right off the end of that. So there's an important message there let me go back. In this program is that if we're going to put stuff into some string variable, we have to have allocated space for it. Now, let's look at one other example here. And this one I see beginning C programmers do a lot. That they'll look up like StringCopy, and they'll say, okay, well, it takes a character pointer as the first element. So I'm going to allocate a character pointer, and then I'm going to copy stuff into that character pointer. Now, this might seem reasonable. It says, well, StringCopy wants a character pointer, so I'll allocate a character pointer variable, and then I'll copy this data into that character pointer because that's what I want to do. I want to store hello world into this thing. But remember, this character pointer is a pointer variable, is a variable that's holding an address. In other words, it's a block of data bytes in memory that stores an address. And just like every other variable, just like I or any other variable I create, if I don't initialize this, it's uninitialized. So what is this pointer variable? What address is that holding? It's just going to be holding random garbage values. In other words, we have a random address in memory stored in this. And now what's the string copy doing? It's saying, hey, go to that random place in memory in the computer system, and let's just copy some bytes into that place in memory. And so essentially what we're doing is we're kind of like playing Russian roulette. This is like saying, hey, pick a random place on my body, and then let's take this pen and let's start jabbing, make a hole in our body and start stuffing like, I don't know, like Scrabble tiles in there that spell hello world exclamation mark. And the problem with that is that we have not allocated a space to actually hold this data. We've allocated no space, and we didn't even initialize this to be pointed at allocated space. So this is just saying write the word hello world in a random place in our computer's memory, which is assuredly not right. Now, fortunately, modern operating systems will detect our program trying to do bad things to the body of the computer, if you want to think about it like that. So the operating system will kill our program rather than let it do dangerous stuff like that. But if you're writing this code on an embedded system for something like let's say an Arduino or some other embedded system device, like my company develops a whole lot of systems that are run on these little microcontrollers that are all programmed in C. If we were to run that code on that, where there isn't an operating system, it'll say, sure, let's pick a random spot in our memory and write hello world in there. And depending on when we run this program, this could get a different address at different times. So sometimes this might look like it works. Sometimes it'll work fine. But for the most part, or other times, it could do something terrible and crash the entire system. And it's dangerous. So remember here, well, let's look at what happens when we run this. Well, we ran this I ran this in a Linux-based system, so it's segfaults, gives a segmentation fault, which is essentially the same error on a Linux system or Unix system that you'd get when if you're running this on Windows, you'd get a thing that says this program has performed an illegal operation and Windows decided to close it. And so essentially the operating system caught us trying to write to a random spot of memory that was not allocated to our process, and it killed it. Would kill that. In this case, it was Linux that saw that. So just program crashes. And so a novice C program would look at this and be like, well, I gave it a character pointer, and I've tried to put hello world in there. What's wrong with that? Well, the problem is we did not allocate space to hold hello world, and we did not initialize that pointer to any value that's to allocated space. So it's going to crash that program. Okay, so to summarize that, with string functions, we have to have space allocated for any string that we're copying or otherwise manipulating. We have to allocate space. It's up to us to do that. We can't just say like you would in Python and say like x equal quote double quote hello world. You can't do that. But we need to copy that into a space that we have allocated space for. Copy that data into there. And it's up to us that even if I have allocated space, that I don't add more things to the end of that string and go off the end of the allocated space. It's up to us to do that. Now, as we'll see later on, you can make something that works more like those other strings by making a function library that handles strings, or when we talk about C++, as an add-on to C, there's a string class we can use that does a lot of that stuff for us. But in straight C, again, it's designed to be a systems programming language, designed to be super, almost hyper efficient and close to what the hardware does as much in a one-to-one method as possible. And so it's up to us to do some of that lower level stuff. Now that sounds harder than it is. You have to have a little bit of discipline when you program in C, and you have to be careful with that. Also, never use a character pointer that isn't pointed at allocated memory, which is what we did back here. This is just pointed at some random spot. We did not allocate memory for it. And one of the things we're going to look at later on is there is a way to do dynamic memory allocation where we can say allocate memory of a certain size, and then later on say, well, I need more memory now to put more things in. Let's allocate this a little bigger, and so forth. All right, now let's look at a couple other string functions. We looked at string length last time, which if you remember, you passed a pointer to the string, and it tells how long that string is. And the way it does that is by counting up the number of spaces until we get to the null, and then it returns that length. And that length does not include the null byte. It's basically the characters up to the null, but not including the null. Now, there's another one that's strnlen, which works the same way, except that we can pass a maximum length. So in other words, we can say, give me how long this is, but never exceed this. So it's kind of like a string length, but if it ever gets to this count, it immediately returns and says, that's the maximum length, and it does not include the null, just like this one. So in other words, this strnlen is the same as this one, but it allows us to put a maximum size on how long it would return to us. And that can be useful for making sure we don't overwrite something. We can say, hey, tell me how long this is up to this amount of size that I have allocated. And if it exceeds that, then we will never get a number out of this that ever goes past that amount. So notice it says it looks at the first max length bytes at S and never beyond S plus max length. And S is the string, pointer to that string. It'll never go past that address when looking at it. Now, a couple other ones. StringCopy copies from one location to another, to destination from source. And it basically copies byte at a time. We used that earlier when we copied that help thing in over the top of Hello World. But you'll notice that that works. There's also a bounded version of that, strncpy, where you pass in the maximum length you want to have it. Now, one thing that I want to point out is if you go to look at the documentation for these functions, sometimes for example, in Unix, the documentation for this will have this one listed as a const character pointer, that const in front of that. That basically means that this is not going to change, this string is not going to be changed by this function. This one not having a const in front of it says the function is going to change that one. So if you see a const in front of one of these arguments, we haven't talked about those yet, but const basically means this argument is a constant that is not going to be changed. The compiler will not allow it to be changed inside of that code. And that tells somebody developing with this, okay, I can pass in this pointer to this thing, and I guaranteed this function is not going to modify this data at that place that I passed in. Another difference you might notice when you look at these is this unsigned int that I have here might say size underscore t. That size underscore t is something that's kind of defined for us. It's kind of the allows for cross-platform compatibility for different systems, and that's basically the type associated with the size of that. It's usually an unsigned int, but on some systems, like a 64-bit system, it might be an unsigned. They're always unsigned. It might be an unsigned long, or on a microcontroller-based system that's a 16-bit processor, an 8-bit processor, that might be a unsigned short int. But the way to abstract that so it works on every system is to do size underscore t, which is just pound defined as, or type def as whatever type it is. So I put an unsigned int there to show this is just a number. And some documentation will have that listed as an unsigned int. All right, anyway, notice that there's a kind of a pattern developing here. There's the normal version of the function, and then there's the one with the n, which stands for the number limited. And notice strcopy, strncopy. And the only difference is we added that one additional parameter on the end, or argument on the end, that says, so this is essentially saying copy from here to there until you get to a null or you get to n bytes at the end. Also notice that it has this warning here that if there's no null byte among the first n bytes, it will not put a null on the end. We would have to do that ourselves. All right, the next one is how we compare two strings. Because in C, you cannot say S1 equal S2 to compare them to see if they have the same string in them. Because if you do that, S1 equal S2 with two character pointers, you're actually looking at the addresses. You're saying, does this address match this other address? But we don't want that. We want to look at the actual bytes. So to do that, there's a function that does that for us, strcmp. And we pass in the pointers to two things. These would both be constant, by the way, because this function does not change anything. It just compares them. And basically what this does is it returns an integer less than 0 if S1 is less than S2. It returns 0 if they're equal, and it returns a number greater than 0 if this one is bigger than that one, kind of alphabetically comparing the two. So in other words, if the two match, you'll get a 0 out of this function. If they don't, think of it like a balance. So if they match, it's a 0. If this one, let me see this from your point of view, if this one is bigger than this one, you get a negative number. If this one's bigger than that one, you get a positive number. And if they're exactly equal, you get a 0. So in other words, you can think of this as like, what's the difference between them? If the difference is 0, they match each other. Now, there's another version of that one too, that strncmp, which compares this with that, but up to that number of bytes. So it'll compare until it gets to a null or to n bytes. So if you wanted to say, hey, do the first 5 bytes of this match the first 5 bytes of that, then you could put a 5 there, and it would only compare them up to the first 5. But it works the same way as this does, other than that. All right, strcat, that's a string concatenation. In other words, take one string and then add on the end of that another string. So what that does is it basically runs through the first string till it sees the null, and then replaces that null with all the bytes of the second string, and then adds the null on the end. But keep in mind that you need to have enough space. Notice it says that here in the description. It says the destination string must have enough space for the result. If the destination is not large enough, program behavior is unpredictable, meaning that it'll run off the end of that buffer. It doesn't check that for us. And also notice that the official documentation says buffer overruns are a favorite avenue for attacking secure programs. So again, if you're typing something in and concatenating that in your program into some statically allocated thing, C is going to let that happen, and you could have somebody inject something that runs off the end of that and puts something into your program, or crashes your program maliciously, or adds something in that injects code in somewhere. So in other words, it's up to us to make sure we don't go off the end. One way to do that is to make sure we use something that's bounded like this. And again, here's a version that says copy this to that up to that many things, but not more than that. Okay, a couple other string functions here. str in the official documentation calls this haystack and that needle. Basically, we're looking for this string in this buffer. So in other words, here's a large string, here's a smaller one. We're saying find the first place where this exists in that. And notice that's what it says. Find the first occurrence of the substring needle in the string haystack. The terminating null bytes are not compared, so all it does is compare up to the null. So in other words, if I had a thing that says hello world, and I search for WO, it would find that, and it would return a pointer to the place where the beginning of that first occurrence was. If it doesn't find it at all, if this pattern is not found on that, it returns a null pointer, a pointer with an address value of 0. Another one that's similar to that is strchr. It finds the first occurrence of this character in this string, and it returns a pointer to where it found that. So if I were typing in hello world, and I said find an O, find the O character, it'll go through that and it'll return the H doesn't match, E doesn't match, L doesn't match, L doesn't match, O matches, return the character pointer, the address of where it found that O. And if it does find that, it does not find that, again, returns a null pointer. Okay, now a couple other related functions that I think it's good to be exposed to. And these are not necessarily string functions, but they're closely related. There's one called memset, which is, we talked about memory not being allocated or not being zeroed out. Well, memset allows us to do that. So we basically give it a void pointer. And what a void pointer is, it's just a generic address. It's not a character pointer, it's not an integer pointer, it's not a float pointer, it's just an address of some sort. So in other words, we could pass in any address type we wanted to this, any kind of address of anything. We're just giving it an address, and then we're giving it a number of bytes, and we're giving it the character we want to set it to. So if I were to say memset this location address with 0 and 10, it would say go through 10 bytes starting at that address and set them all to 0. So you can use this to fill a block of memory with some value. And one thing you might want to think of this as is like you have some buffer in memory that's representing pixel data on the screen, and you want to clear that all out, make it all black. Well, you could point this at that buffer, put in a 0 here, put in the number of pixels that are on the, or bytes that are associated with pixels on the screen in here, and run this one function, and that would clear the entire buffer out. Now, another thing that's similar to that is this memcopy function. And memcopy copies one block of, it's like StringCopy, but it doesn't really care about the null character. All it does is say copy this block of data that's at this address to this address here, and this is how many to copy. So in other words, copy from one place in memory to another place in memory. And you can think of that kind of like blitting pixels into a spot in memory onto a display surface or a screen. So here's this image that's off screen, copy it onto the place that's associated with the screen with memcopy, and it'll just buzz through memory and copy this number of bytes there. Another one that works kind of like string compare if you want to compare two things in memory. Mem compare, mem CMP, that will say go to this address, go to that address. Notice I left the const in that one. Go to this address, go to that address. Actually, these should both be const. Here, let me take that out just to avoid confusion. We don't need that to understand what it does right now. All right, so go compare this place with this place, just like with string compare, this number of bytes, it produces a 0 on match, a negative number if this is smaller than that, a positive number if this is larger than that. All right, now the second little bit of this that I want to go through quickly is this function organization. And I've noticed some difficulties in the questions that's being asked to me in how people are organizing their code into functions. So I'm going to give you some a few quick tips and some rules here. So the first one, rule 1, functions, and here I'm going to turn off my, you can't see what that says right there, so I'm going to turn off my face here for just a second. All right, so rule 1, functions must have a prototype or be defined before they're called. And here, let me just fix this, and I can turn the, oops. All right. Now I'm kind of running into that. Hold on one second here. All right, let's try that. All right, now I can maybe turn my face back on. Not that it really matters if you can see me or not, but hi. All right, anyway, rule 1, functions have to have a prototype or be defined before they're called. Now, have to or must here is a little bit of a strong word because the compiler will let you do that, but it'll bitch at you. It'll warn you. It'll say, hey, this function doesn't have a prototype, so I'm kind of guessing what to do with it here, and I don't know if I'm guessing right. But for a proper C program that does not have warnings and does not have the potential for a disaster, you should always have a prototype or define the function first. So here are those two methods. Here's a prototype. And you notice what a prototype is it looks like this first line of the function, kind of the thing that describes the return value and the arguments or parameters that pass in, has the name. It looks exactly like that, but with a semicolon at the end. And what that says is when the compiler is running through this, it says, okay, there's going to be a function called f1, and that has these things passed to it, and it returns this type. So when you see f1 being used, you can check to see if it has the right things passed to it, and that the type of it is being used correctly and matches with the way it's being used. And if we don't have this, the compiler will come across f1 and says, I don't know what f1 is, so I'm just going to guess what it is. And it might guess right, it might guess wrong, and that's why you get that warning when you do that. So we should always have a prototype at the top so we're not just relying on the compiler to figure things out for us that it might guess wrong on. Now, if you do it this way, then you can define your functions down here. You can put your prototype up here, and then the first thing you'll see after the pound includes and the functions and the global variables, whatever, would be our main. And that's typically the way it's done because that puts the main part of the program at the top, which is useful. You can say load a program, and you can go down to main and say, okay, this is what it's doing, not have to wade into all of the code that's below here with the support functions first. And notice that's a little bit different than Python programs. In Python programs, you write a bunch of functions. They have to be defined at the top, and then your main is toward the bottom. But that means you got to wade through all that stuff and scroll all the way to the bottom to find where the main part of the program is. But in C, the typical way is to do this. But if you wanted to, you could get rid of the function prototype altogether, define the function up here at the top, and then use it. And now that when it comes across, it says, okay, I know what that is, so I saw what that function looked like because it was defined up here. So you have to do one, you should do one or the other. The one on the left is preferable. And it's typical among C programmers. That's rule 1. Rule 2, Functions have to have a prototype. Actually, is this, this is just labeled wrong. Let me fix that real quick, and let me fix the layout of this. So functions should not be nested within other function definitions. So in other words, here's your prototype, here's your main function, here's your F1 function. If you had another function F2 prototype, you have another function F3, you would have its prototype and its definition down here. You can list any of those down there as you want. So do that. Do not define your function inside of the main function. And C++ allows that, and there are extensions to GCC that allow that, but that's not standard C programming practice. Every function should stand on its own, be defined on its own, not be defined within another function. So do not do this over here. It's not standard practice, and it really isn't good practice. Do this. This function stands on its own. It gets called from F1. We don't want to define it inside of main and then call it from inside of there. All right, rule 3. The function prototype has to match the function definition. So in other words, if I do something like this and say this, okay, F1 is returning an integer and I'm passing in this unsigned integer down here. And then in my function definition, I say void and put that, then it's going to try to compile, it's going to try to generate the code for this, and then it's going to come across the actual function definition. It's going to be like, that does not match that, and it won't let it compile. So we have to make sure that the function prototype matches the definition of the function. The compiler will not let it compile if those don't match. It'll say something like function F1 redefined. It'll see this as, this is different than that. We redefined something in a way that doesn't make any sense to what I knew. You told me the function was going to look like this, and then you made a function that instead of an integer, it returned a character, and instead of returning an integer, you passed a character, and instead of returning an integer, you said it didn't return anything. So we have to make those match. Rule 4. For organization of your code and libraries, when you start getting a lot of functions, rather than having a program like this where there's just hundreds or dozens of functions in that and dozens of prototypes at the top, to organize that, you can gather all of these functions that are kind of alike into their own C file, and then use them in your main program like we are here. But we still need the function prototype. So the typical way of doing that is to put them in a header. So we would organize our functions in a .c file, and we'd put the function prototypes in a .h file. And so here's an example of that. So here's funcs.h, where I define function F, I have the function prototype. Again, the same line that would make this up, but with a semicolon at the end. And there's function F1, function F2, function F3. And in practice, you might organize those as like npc_ai.h. And here we would say something like wander and flee and whatever else we'd attack, whatever else the talk, whatever functions we had that those things were capable of doing. We would gather the function, just the function prototype, so not the code for the functions in the .h file. You never want to put code in your .h file. And then in your .c file, we'd have the actual implementations. And then at the top, we can include funcs.h, which then puts the function, all the function prototypes at the top up here inside for all these. So if these need to call each other, they have a function prototype to know how to call each other. But notice this is very clean now that we have the function prototypes over here. We have the function definitions over here. We're using the prototypes that are in the .h file. And the cool thing about doing that is now to use that in our main.c, we don't have all those functions listed after main. We just have main. So here's just main. And to use that, we just need to pound include funcs.h, and then we can call those functions because now the compiler knows what those look like. And the linkers, if this is in our project, the linker will now link all those things up and use them. So this is the kind of organization system that you want to move towards when you get to a larger project. If you're doing something small, then something like this is fine where everything's contained in one source file. But when you get to something larger like a game or a business system or something for an operating system, you're going to want to organize your code into, like, this is the AI stuff, this is the math stuff, this is the physics library, this is the, I don't know, the network code. You don't want to put all that in one giant, like, million-line main program. You want to put that into the separate things. You say, I'm having a problem with the network code. I'll look at the network source file. And if I want to add a function to that, I just add the prototype to the funcs or the header file for that, network.h or whatever, and then I add my functions in here, and then I change how main calls those. So that's the way you want to go about organizing your code when you get to larger projects. For right now, for the projects we're doing for the labs, you can just put it all in one source file like this. But later on, when we get to more complicated things, you're going to probably want to divide those up. And actually, in future labs, that's going to be part of the what the lab requests that you do. It's going to say, organize your code like this. Okay, so that's all for today. Go and try to finish up those labs. Make sure to check for quizzes as those come up. And everybody stay safe. Wear a mask when you go out. If you're an anti-masker or a COVID denier, stop being stupid. A lot of people have died from COVID, and including people I know. And last night, a college student died in North Carolina, otherwise healthy, no pre-existing conditions. So make sure to stay safe and be smart. Wash your hands. And if you need help, send me a text message or talk to me on Discord, or give me a phone call, or send me an email. Email always works well. If you're asking questions about your code, make sure to include a snippet of the code that you have the question out, or just copy and paste your code in. I'm happy to take a look at that and help. And if you need me to, I can certainly come down to the university. I'll actually be down there today for a little bit. So if you need help or have questions on things, feel free to stop by my office today. I'll be down there from 4:15 to 5 for my office hours. And my building is only a block away from the university. So if you need me to come in on a Friday or a weekend or any other time, just let me know. We can schedule something. I can come in and help you if you're struggling. All right, so that's it. Everybody stay safe, and I'll see you next time.